the final lecture of week 1 on first order systems and first order circuits. So far we have looked at deriving the governing differential equation, the static gain, and the time constant for first order systems and first order circuits, as well as analyzing first order circuits in order to find the governing differential equation, the static gain, or the time constant. We will continue our analysis of solving first order circuits which have a step input such as a u of t, but we will also look at circuits that have arbitrary inputs using integrating factors. We will also analyze circuits which have switches or step functions as well, because as we talked about in lecture 1-2, a step function is a way of representing a switch opening or closing on a circuit. For the following circuit, assume the switch has been open for a long time. Open for a long time implies DC conditions or steady state conditions, which means you model that with the capacitor under DC conditions as an open circuit, and it closes at t equals 0. So when it closes at t equals 0, that's where the transient or the circuit starts changing because voltage is charging or discharging across the capacitor, and determine V of t after the switch moves. So the task here is to find tau, find V of t, find k, and also find the governing differential equation. Note that the input would be the voltage source, or in this case the two voltage sources, and the output is V of t, the voltage across the capacitor. Recall that the general equation is tau dy of t dt plus y of t equals k x of t, and the general solution is y of t equals ka plus y of 0 minus ka e to the negative t over tau, or in terms of time, y of t equals y of infinity plus y of 0 minus y of infinity e to the negative t over tau. So the first thing we do is we draw the circuit at t equals 0 minus under DC conditions, and we use that circuit to find the initial voltage across the capacitor, V of 0 minus. Now this symbol means that the switch closes at t equals 0, which means at t equals 0 minus, the instant right before that time, the switch is open. So the circuit looks like 10 volts, 2 ohms, DC condition, so the capacitor is an open circuit. Here is V of 0 minus, and here's the open switch, which means the 6 ohm and the 50 volt source are actually not connected and don't affect the analysis at this point. So since this is an open circuit, no current flows through the 2 ohm resistor. V of 0 minus is equal to 10 volts. Then we draw the circuit at t equals 0 plus. That means the switch is closed. And we use this circuit to find tau. Remember, this is an RC circuit, so tau is equal to R Thevenin times C. So if the switch is closed, we have the 10 volt source, 2 ohms, 6 ohms, the capacitor is here, 1/3 of a farad, and the 50 volt source. However, to find R Thevenin, we turn off sources. So if I short out the 10 volts and the 50 volts, and we have 2 ohms and 6 ohms, the Thevenin equivalent resistance seen by that capacitor is the 2 ohm resistor in parallel with the 6 ohm resistor, 12 over 8, or 3 over 2 ohms. So tau is equal to R Thevenin times C, 3/2 times 1/3, which is equal to 1/2. And now we analyze the circuit after a long time, or t equal infinity. So this is once again DC conditions. And we use this circuit to find V of infinity, and the switch is still closed. So we draw the circuit, and remember the capacitor looks like an open. I have 2 ohms, 6 ohms, 50 volts, 10 volts. There's my open. And I want to find the voltage across here, V of infinity. There are several ways to do this problem. Probably one of the easiest is to just do KVL, the sum of the voltages around the loop, where we label the loop current I. And what I have is -10 plus 8I minus 50 equals 0. 8I equals 60. So I is equal to 60 over 8, which reduces to 7.5 amps. So V of infinity is equal to 6 times 7.5 minus 50, or V of infinity is equal to -5 volts. So now we have all the information we need in order to write the equation. Y of t is equal to Y of infinity, -5 plus Y of 0, 10 minus Y of infinity, plus 5, e to the -t over tau, which is e to the -t over 1/2. So this reduces to the output voltage V of t is equal to -5 plus 15 e to the -2t volts. And it's very important to emphasize that this is only the voltage for time greater than or equal to 0, because we know at time 0 minus it was 10 volts. So this basically shows what happens is that once that switch closes, this capacitor, which had charged to one value, immediately starts charging to a different value. The way you would show that on a graph is that here's V of t, here's t, and the initial voltage is 10 volts, and it starts to die off, and as it approaches infinity, it's going to reach -5 volts, and the time to go from 10 to almost -5 is 4 time constants. All right, let's try another example. Determine VC of t for the following circuit if IS of t is 0 amps for t less than 0, 2 amps for t between 0 and 1 second, -3 amps for t between 1 and 2 seconds, and 1 amp for t greater than or equal to 2 seconds. So the input is a current source, IS of t, and the output is the voltage across the capacitor. So first, let's make a sketch of VC of t. The horizontal axis is time in seconds. The vertical axis is VC of t in volts. And for t less than 0, we have 0 amps. And then between 0 and 1, it jumps up to 2 amps. And then between 1 and 2, it jumps down to -3 amps. And then for greater than 2, it goes to 1 amp. So here's our -3. And then at time 2, it jumps up to 1 amp for the rest of the time. So this is a piecewise linear function. So if we think about intuitively what we think is going to happen, this is like switches turning on and off with different values. So it'd be a 2 amp current source, then it turns into a -3 amp current source, and it turns into a 1 amp current source. So every time that happens, the capacitor is going to be trying to charge or discharge to a different value. And it's going to be represented by these exponential functions, which we will see after we do the calculations. So first thing we're going to find is the static gain, K. Remember, the static gain K is VC of infinity over IS of infinity. So VC of infinity means steady state conditions, which means we have an open circuit here, so there's no current flowing through the 20 ohm resistor. So at that point, the relationship between the voltage and the current is the relationship between the voltage across the 10 ohm resistor. So VC of infinity over IS of infinity is a gain of 10. Tau is equal to R Thevenin times C. The Thevenin equivalent resistance seen by the capacitor, remember you turn off all independent sources to find Thevenin equivalent resistance. This becomes an open circuit, would be the 20 ohm in series with the 10. So that's 20 plus 10 times the value of the capacitor, which is 0. So tau is equal to 3 seconds. And VC of t is equal to K plus VC of t naught minus Ka e to the negative t minus t naught over tau. So substituting in the values we found for K and tau, we have 10A plus VC of t naught minus 10A e to the negative t minus t naught over 3. And this is the same equation we will use for each of these intervals to analyze the circuit. So the first interval is t less than 0. For the interval t less than 0, since the input is a 0, the output would be a 0. So VC of t is equal to 0 volts. The next interval is for t between 0 and 1 second. The interval between 0 and 1 second, t naught, the beginning time, is 0 seconds. The amplitude of the source at that point, A, is equal to 2. And because voltage is continuous across all time intervals, since it was VC of 0 is equal to 0, VC of 0 plus the time right after would also be 0. So VC of t is equal to 20 times 1 minus e to the negative t over 3 volts. So now we'll do the next interval, which is t between 1 and 2 seconds. For this interval, t naught is equal to 1, A is equal to negative 3, and now we have to find the voltage at the beginning interval. So this would be VC of 1. VC of 1 is going to be 20 times 1 minus e to the negative 1/3. So VC of 1 is equal to 5.67 volts. So VC of t is equal to K times A, negative 30, plus VC of t naught, 5.67, minus Ka, so that becomes plus 30, times the interval e to the negative t minus 1 over 3, which simplifies to negative 30 plus 35.67 e to the negative t minus 1 over 3 volts. And the last interval is t greater than or equal to 2 seconds. So for this one, t naught is equal to 2, A is equal to 1, and VC of 2 is equal to negative 30 plus 35.67 e to the negative 2 minus 1 over 3. So VC of 2 is equal to negative 4.49 volts. And we now have all the values we need in order to write VC of t. So VC of t is equal to 10 plus negative 4.49 minus 10 e to the negative t minus 2 over 3, which simplifies to 10 minus 14.49 e to the negative t minus 2 over 3 volts. So if we were to make a sketch of what VC of t looks like given IS of t, before time 0, it would be 0. And then it would start charging up to a final value of 20. But it's never going to get there because switching happens at 1 second. So it stops at 5.67. And then it starts to discharge. And it's trying to discharge to a final value of negative 30. But once again, it's never going to get there because switching is going to happen again at 2 seconds. So it's going to go to negative 4.49. And then switching happens again and it starts charging again. At this point, it's trying to charge up to a final value of 10. And as long as it stays there long enough, it will get there. And the time that it takes to get to the 10 will be approximately 5 time constants. And since our time constant is 3 at about 17 seconds, because 5 tau would be equal to 15 seconds, it would actually get to 10 volts. Since students sometimes struggle with this concept, I would like to do a couple of supplemental examples before moving on to the next topic in lecture 1-3. Let's look at another circuit that is also an RC circuit, and we want to find V of t. In order to do this, we're going to use the following equation. V of t is equal to V of infinity plus V of 0 plus minus V of infinity e to the negative t over tau. Notice that the switch moves from the left side, or node 1, to node 2 at t equals 0. So we know that t naught is equal to 0. And we also, in order to solve this problem, are going to need to find the initial voltage across the capacitor. And we're also going to need to find tau, as well as the final voltage across the capacitor if its switch moved to position 2 and stayed there for a long time. So the first thing we do is we analyze this circuit at t equals 0 minus, when the switch is at position 1 and the circuit is under DC conditions. And we use this analysis in order to find the initial voltage across the capacitor, or to find V of 0 minus. So looking at only the left side of the circuit, we're going to have 40 volts, 20 kiloohms, 60 kiloohms, and under DC conditions, we model the capacitor as an open circuit. So it's here, and this is V of 0 minus. Now note that there is more parts of the circuit, but because they're not connected yet, they don't affect the analysis, so I won't bother to draw them. V of 0 minus can be found by using the voltage divider. V of 0 minus is the same as the voltage across the 60 kilo ohm resistor. So that's 60 over 80 times 40. So V of 0 minus is equal to 30 volts. Now we draw the circuit at t equals 0 plus. The switch has now moved to position 2. We no longer have DC conditions, and we use this circuit to find tau. So when the switch moves to the other side, I have the capacitor here, 0.25 microfarads. I have an 8 kilo ohm resistor, a 40 kilo ohm resistor, a 160 kilo ohm resistor, and that 75 volt source. Tau is equal to R Thevenin times C. The Thevenin equivalent resistance seen by the capacitor is found by turning off any independent sources. So in this case, if I turn off the independent source, I have the capacitor and I have the 3 resistors. And the voltage source is shorted out. So I have 8 kilo ohms, 40 kilo ohms, and 160 kilo ohms. So our Thevenin would be equal to 8 plus 160 and parallel with 40. So our Thevenin is equal to 40 kilo ohms, and tau is equal to 40K times 0.25 micro. So tau is equal to 10 milliseconds. At t equal infinity, the circuit is back under DC conditions, and the switch is still at position 2. So since we have DC conditions, the capacitor looks like an open circuit, and I'm looking for the voltage across it, which is V of infinity. And I have the 8 kilo ohm resistor, the 40 kilo ohm resistor, the 160 kilo ohm resistor, and the 75 volt source. Since I have an open circuit, there is no current flow and no voltage drop across the 8 kilo ohm resistor. So V of infinity is the same as the voltage across the 160 kilo ohm resistor. So V of infinity can be found from the voltage divider, and it is 160 over 40 plus 160. And because the polarity is reversed between the voltage source and V of infinity, it's negative 75. So V of infinity is equal to negative 60 volts. Okay, so we are finally ready to write V of t. V of t is equal to V of infinity, negative 60, plus V of 0 plus 30, minus V of infinity, negative 60, e to the negative t over tau, and in this case, tau is equal to 10 milli. So if I simplify this, we can write this as negative 60 plus 90, e to the negative 100t. The units are volts, and because this is the voltage for t greater than or equal to 0, I put this at the end. And now let's make a sketch of what this looks like. So the initial voltage across the capacitor is 30. Then when the switching occurs at time 0, the capacitor starts to discharge, and it's discharging to a final value of negative 60. And it's going to take about 5 time constants to get there. So when it gets to 50 milliseconds, it will be within 95% or within 5% of negative 60 volts. All right, here's one more supplemental example before we move on. For the following circuit, find an expression for I of t for t greater than or equal to 0. And notice this is a different kind of switch. It's called a make before break switch. What this means is that when the switch moves from position A to position B at time equals 0, it has to make position B before it breaks position A. The reason this is important is because we have an inductor, and the voltage across an inductor is L di dt. So if position A were to break before connecting with position B, that would be a huge spike in the voltage because the current would go to 0 for that very small instance of time. So that's the distinction between this type of switch and the ones we've seen up to this point. So once again, our output is going to be I of t. And the input is going to be that 24 volt source and the 8 amp source as it moves from 8 amps to 24 volts. So it's still a step. And we're going to try to find, in order to solve this problem, I of 0 plus, I of infinity, tau in the governing differential equation. So the first thing we do is we draw the circuit at t equals 0 minus when the switch is at position A and we have DC conditions. So at that point, I have an inductor that looks like a short circuit because we have DC conditions. I label the current through it, I of 0 minus. We have the 10 ohm resistor and the 8 amp current source. Now, since the inductor shorts out the 10 ohm resistor, it's like it's not there, which means that the current through the inductor, I of 0 minus, is the same as the current source, but since they're going opposite directions, the current would come up through the inductor as opposed to going down, so I of 0 minus would be negative 8 amps. Now let's go on to t equals 0 plus. T equals 0 plus, the switch moves to position B, and we use this circuit to find tau. Recall that tau is equal to L over R Thevenin. So we redraw the circuit and we're trying to find the Thevenin equivalent resistance seen by the inductor. So we have 24 volts, 2 ohms, and 200 millihenry. And the good news is there's only one resistor, so R Thevenin is easy. R Thevenin is 2 ohms. So tau is equal to 200 milli divided by 2, or tau is equal to 100 milliseconds. And now we draw the circuit at t equal infinity. The switch is still at position B. We have DC conditions. And we use this circuit to find I of infinity. So I have the 24 volt source, the 2 ohm resistor, the inductor modeled as a short, DC conditions. So here we have I of infinity, and using Ohm's law, I of infinity is equal to 24 divided by 2, which is equal to 12 amps. Finally, let's write I of t. I of t is equal to I of infinity plus I of 0 plus minus I of infinity times e to the negative t over tau. So I of t is equal to 12 plus negative 8 minus 12 e to the negative t over 100 milli, which simplifies to 12 minus 20 e to the negative 10t amps, and this is I of t for t greater than or equal to 0. An alternate method for determining the solution to a first order circuit is to use integrating factors. Later in this quarter, we will use frequency domain and sinusoidal steady state analysis, or Laplace transforms, to determine the solution to first order differential equations with arbitrary inputs. Integrating factors are used when you have any type of input, not just step inputs. So far, everything we've discussed is only applicable to step inputs. Solving an ordinary differential equation with integrating factors is based upon the fact that an ordinary differential equation can be multiplied by a function to make it integrable. Let's examine a general differential equation given by dy of t dt plus p of t y of t equals bx of t. In order to find a function to solve the differential equation, multiply both sides by an arbitrary function a of t. And this yields a of t times the derivative of y plus a of t times p of t times y, which equals b a of t x of t. If the product of a of t, p of t represents the derivative of a of t, then the left side of the equation represents the derivative of a product and can be written as the first derivative of a of t y of t is equal to a of t y dot of t plus a dot of t y of t. Recall this is only true if a dot of t is equal to a of t times p of t. Solving for p of t yields p of d is equal to the derivative of a divided by a. Integrating both sides of equation 5 yields the integral of p of lambda d lambda is equal to the natural log of the magnitude of a of t. Raising both sides of equation 6 to the exponential yields the integrating factor, which we will use extensively in this class. A of t is equal to the integral of p of lambda d lambda, or e to the phi of t. Therefore, to solve an ordinary differential equation using integrating factors, multiply both sides of the equation by the integrating factor, and then integrate to solve for y of t. And the solution has the form y of t is equal to y of t naught raised to e to the negative phi of t minus phi of t naught, plus the integral from t naught to t, e to the negative phi of t minus phi of lambda, bx of lambda d lambda. Please memorize this last equation. We use it extensively in class. Next, we will show that we can use integrating factors to solve the standard form of the governing differential equation for first-order circuits that we've studied in prior lectures, and that you actually get the same answer. The first step is to rewrite the standard form to look similar to equation 1. The first derivative of y with respect to t plus 1 over tau y of t equals k over tau x of t. So the integrating factor a would be equal to e raised to the integral of 1 over tau dt, because that represents p of t in this equation, which equals e phi of t, or e to the t over tau. Multiply both sides of the standard equation by the integrating factor, and this yields e to the t over tau dy dt plus e to the t over tau 1 over tau y of t, which equals e to the t over tau k over tau x of t. So now we rewrite the left side as the derivative of a product as we did before, and you get the derivative with respect to time is e to the t over tau y of t equals e to the t over tau times k over tau x of t. Integrate both sides of equation 4 from t naught to t, which yields y of t is equal to y of t naught e to the negative t minus t naught over tau, plus the integral from t naught to t, e to the negative t minus lambda over tau, k over tau x of lambda d lambda. Show that this equation reduces to the general solution in the last lecture if t naught is equal to 0 plus and x of t is equal to au of t. So we're going to have y of t is equal to y of 0 plus e to the negative t over tau, and this is replacing t naught with 0 in both places, plus the integral from 0 plus to t, e to the negative t minus lambda over tau, k over tau. Remember, x of t is au of t, so this becomes a d lambda. So the next step is we're going to evaluate the integral y of 0 plus e to the negative t over tau plus, and now we're going to factor out ka over tau and e to the negative t over tau. So left in the integral, we have the integral from 0 plus to t, e to the lambda over tau d lambda. So the next step, we're going to actually find the integral. So we have y of 0 plus e to the negative t over tau plus ka over tau e to the negative t over tau. And when we take the integral of e to the lambda over tau d lambda, this yields tau e to the t over tau minus tau. So now we're going to collect like terms. So we'll have y of 0 plus e to the negative t over tau plus ka minus ka e to the negative t over tau. And finally, y of t is equal to ka plus the quantity y of 0 plus minus ka e to the negative t over tau. And we should recall that this is the equation that we had before. So now let's do a couple of examples that use integrating factors, and this is where we will end the lecture for today. So use integrating factors to solve for the general solution of the ordinary differential equation y dot of t equals the cosine of t y of t x of t minus 1. So recall from the form that we had on the other page, p of t in this case is the cosine of t. So the integrating factor a of t would be equal to e raised to the integral of p of lambda d lambda, or e raised to the integral cosine of lambda d lambda. The integral of cosine is sine, evaluated from 0 to t. So in this case, our integrating factor is e to the sine of t. So remember, the next step is to multiply the equation left and right side by the integrating factor. So we have e to the sine of t, y dot of t, plus e to the sine of t cosine of t, y of t, equals e to the sine of t x of t minus 1. So remember, this left side can be written as the product, the derivative with respect to time, of e to the sine of t, y of t. And we set that equal to the right side of the equation, e to the sine of t, x of t minus 1. Now, the next step is to integrate both sides of the equation from t naught to t. When we integrate the left side, because it's the integral of a derivative, we end up with e to the sine of t, y of t, minus e to the sine of t naught times y of t naught. And on the right side, we keep the integral. So it's the integral from t naught to t, e to the sine of lambda, x of lambda minus 1, d lambda. So when we solve for e to the sine of t, y of t, we have on the left side e to the sine of t, y of t, equals to, on the right side, e to the sine of t naught, y of t naught, plus the integral from t naught to t, e to the sine of lambda, x of lambda minus 1, d lambda. Now we're almost done. The final step is to solve for y of t. You can solve for y of t by dividing both sides by e to the sine of t. So the final answer is y of t is equal to e raised to the sine of t naught minus the sine of t times y of t naught plus e to the minus sine of t times the integral from t naught to t, e to the sine of lambda, x of lambda minus 1, d lambda. Use integratings's to solve for the general solution of the ordinary differential equation 1/2 y dot of t plus y of t equals e to the minus t x of t. So the first thing we need to do is to rewrite this differential equation in the form so that we can quickly identify p of t. So I'm going to multiply the left and right side by 2, and we're going to have y dot of t plus 2y of t equals 2 e to the minus t x of t. And comparing this to the equation we had before, p of t is equal to 2. So the integrating factor, a of t, is equal to e raised to the integral of p of lambda d lambda, or in this case, e raised to the integral of 2 d lambda from 0 to t. So the integrating factor is e to the 2t. So now let's multiply both sides of equation 1 by the integrating factor, and we have e to the 2t y dot of t plus 2 e to the 2t y of t equals 2 e to the t x of t. So now remember, we can write the left side of the equation as the derivative of a product. So it's going to be the derivative of e to the 2t y of t, and that equals to 2 e to the t x of t. And now we're going to integrate the left side of the equation from t naught to t and the right side of the equation from t naught to t. So because the left side is the integral of a derivative, we're going to have e to the 2t y of t minus e to the 2t naught y of t naught, which is equal to the integral from t naught to t, 2 e to the lambda x of lambda d lambda. So now we need to solve for y of t. So the first thing I'm going to do is add e to the 2t naught y of t naught to both sides of the equation. So I have e to the 2t y of t is equal to e to the 2t naught y of t naught plus the integral from t naught to t 2 e to the lambda x of lambda d lambda. And now I'm going to divide both sides of the equation by e to the 2t, and I'll have y of t is equal to e raised to the negative 2 times t minus t naught y of t naught plus e to the negative 2t times the integral from t naught to t 2 e to the lambda x of lambda d lambda. And this concludes lecture 1-3 on solving first order differential equations by using integrating factors and with step inputs.